Okay, so welcome back for part three. In this section, we're going to take a look at graphing some surfaces. All right, so as I said before, in this section, we're going to take a look at what happens when the functions that we graph become more complex. So we're going to take a look at some complex functions and what their graphs would look like. Technically, all graphs in three-dimensional space are called surfaces. So those planes we were graphing a moment ago in part two, those are surfaces. They are just a simple, uncomplicated surface. Right? In this section, we're going to take a look at graphing more complicated surfaces. Surfaces that can look more like this one over here, where we've got a moving top to this, and there's a bunch of points on that surface, and those points all have an x and a y and a functional value. This is what we would think of as the z value, right? And then we've got an equation that we use to find those z values from those known domain values of x and y. And those x and y values are down there in that xy plane. That's our domain. And then the height, the z, if it's positive, we're above that plane. If it's negative, we're below that plane. And what is it going to look like when we got this weird equation with all this movement? Well, originally, of course, these things were always done by hand. And one of the by hand techniques for graphing these is to take a look at something called the trace, or more correctly, the traces of the function. The traces of the function are found by setting one of the variables equal to 0. Effectively, what we're doing is we're finding what the surface looks like when that three-dimensional surface goes through a two-dimensional plane. So for example, if we set z equal to 0, what we're saying is when this plane, like this corner over here or this corner over here, when that thing continues to dip down and when it passes through that xy plane that's down here, what will that image look like when it passes through there? Okay. But there's three planes that we can look at. We can look at the xy plane, we can look at the xz plane, and we can look at the yz plane. And so because there are three planes that we can look at, there are three traces that we can do. Okay? Every trace that goes through a plane is when the missing variable has been set equal to 0. So if you're looking for the xy plane, there's no z, so that means z is 0. If you're looking for the yz plane trace, that's when x is 0. And if you're looking for the xz plane trace, that's when y is 0. And so let's take a look at an example, and we'll see if we can make some more sense of it. Okay? All right, so what I'd like to do is I would like to find the traces of the function f of xy equals 2x squared plus 2y squared. Now over here I've already graphed them for us, but let's take a look at the math behind what's going on. Okay? If I want to find the xy trace, that's going to be when z is 0, and that's going to be what happens to the equation when we set z equal to 0. So when we set z equal to 0, I get 0 equals 2x squared plus 2y squared. And now what I'm going to do is I'm going to solve this equation for all the values of x and y that make it true and see what that looks like. Well, one thing I learned back in algebra is that the only way that a squared variable is ever going to be 0 is if the variable itself is 0, and for all other values, when you square it, it's going to be a positive number. So this equation can only ever be true at the ordered pair 0, 0. Because for any other value of x other than 0, this will be a positive number. For any value of y other than 0, this is going to be a positive number. And a positive number plus a positive number can never be equal to 0. So the xy trace is a single point, and that represents that point right down there, the origin of the entire thing. Now, if I do that again, and take a look at the other two traces. So I'm going to need to clear some space out, so I'll get rid of this. Let's see, this is in the way. Delete. There we go. I'm going to move this up to here. Okay. If I were to look at the, let's do the YZ trace. Well, that's when x is 0. So if I take that a function and I set x equals 0, I get that z is equal to 2y squared, which means I'm looking at a parabola. And so the red parabola here is going to be that trace. Right, do you see a parabola in there? Right? And I know what you're thinking, parabolas are like this, y equals x squared, right? But a parabola is dependent equals independent squared. Dependent, independent. So it's a parabola just with z's and y's instead of our traditional y's and x's that we were taught in our college algebra class. And then if I try to do the other trace, let's see, I did the xy trace, I did the yz trace, so I'd be looking at the xz trace. So that's when y equals 0. If I set y equals 0, I get the equation z equals 2x squared. So it's another parabola, and that's that blue parabola there. So now I'm supposed to somehow look at this picture and say, okay, it only touches there at one point. That was my x, y trace. This was my yz trace, that parabola. The green one over there is my xz trace. And I'm somehow supposed to take this framework and put it together and figure out what this thing looks like. Well, I don't know that I have enough information. So what I'm going to do is I'm going to use another set of things, another set of helpers, I guess we'll call them, some graphing tools that I can find. And that's going to be what we call our level curves. Now, a level curve for a graph is a value found when we set z equal to various values and examine the resulting things. What does that mean? We do things like this. We say, well, if z was 1, what would this shape look like? If z was 3, what would this shape look like? And so level curves end up looking like this. Now, I know that this graph looks crazy right now, but let's put some perspective on it. Basically, what we're doing is we're looking straight down. So right here, that's the z-axis, but we can't see it because we're looking straight down it. This is the x-axis, this is the y-axis, and each of those circles is a different level curve or a different z value. So if you remember, our original equation was z equals 2x squared plus 2y squared, right? So if I told you that z equals 1, then you'd say, okay, that means that 1 equals 2x squared plus 2y squared. Or if I simplify that, I get x squared plus y squared is equal to 1/2. Now, if you think back to your college algebra, that means that we're looking at a circle, and that's the radius squared. So then the radius would be the square root of 1/2. And so for every different value of z, I'm going to get a different circle because the z here is just going to make bigger and bigger circles. So now I'm supposed to put together these traces up here and these circles down here and kind of build a framework, right? So when I take those circles and I move them up into that graph, that means that as I move up the z-axis, I'm going to get different size circles coming in. So when z is equal to 1, I get a circle. When z is equal to 2, I get a circle. When z is equal to 3, I get a bigger and bigger and bigger circles. And are you starting to get an idea of what that thing would look like in three-dimensional space now? And hopefully you're seeing something like this, which again is hard to see. So let's go over to that website I was using and let's put this thing in. It was z equals 2x squared plus 2y squared, and there's my shape. So let's make that go away. Let's make this bigger. And do you see the kind of, I don't know what you would call that. I know what it's called in space. It's called a paraboloid because it is oh wow, somehow I made that thing spin and also kind of rotate around all at the same time. That's pretty cool. But it's basically just a parabola that has been spun around. Now you might be looking at this and saying, oh, that's really, really cool. Or you might be looking at this and saying, I really don't care. And I get it. Let's talk about something interesting about these. There's something very interesting about this shape. Inside of here somewhere, and I don't know exactly where it is. I could do the math and figure it out. But somewhere in there is a point called the focus of that parabola. And one of the interesting things about a parabola is if something is dropped in this direction, parallel to that z-axis, when it hits the wall and it bounces off that wall, it will always reflect exactly to that focus, no matter where it's dropped in. When it hits, it bounces back to the focus. Whoops. When it hits, it bounces back to the focus. When it hits, it bounces back to the focus, which is pretty cool if you think about it in reverse. Instead of thinking of things going to that, make that be a light bulb. And then coat the inside of this parabola with a mirror. And then what you have is you have the focusing part of a flashlight or a headlight on your car, where it reflects the light out in front of you. Okay? So cool things, lots of neat shapes that we get in three-dimensional space. If I want to graph the surface for some sort of a function, if I needed to do things by hand, that's how I would do them. I would look at those traces. I would look at those level curves. I would see what they give me. But realistically, if I want to know what this is going to look like, I'm going to find a grapher and graph it. Okay, so I've got a y squared minus x equals z. So let's get rid of this one. My equation is z equals, oh man, I forgot already. Was it y squared minus x? Y squared minus x, I was right. Y raised to the second minus x. And there we go. Now, if you look at it, you can see the parabola that's hiding in there. Do you see the parabola from the y squared? And if you look at the bottom edge of that parabola, do you see the line for negative x? And then what we're doing here is we basically put the parabola and the line together. The y squared gives it a parabola shape. The negative x gives it that angle for the line. And you get this kind of a trough. Now they call these parabolic cylinders. I know what you're thinking, a cylinder's round. Yes, until it becomes a parabolic cylinder, then it gets shaped like this. It's kind of like a gutter, a trough, if you will. And that's how we would graph these things. That's how we would come across this. Now, if you look carefully at this, you can see where when they graph this thing, do you see the shadow here, oops, yes, that's a good view. Do you see that shadow? That's the trace. That's the xy trace when z equals 0. And that's that parabola. That's the only trace that you can easily see in this shape, but it's in there, it's hiding in there. So there's lots of neat shapes going on here. There's lots of neat stuff going on here. These are surfaces. All right. There are some surfaces that are common enough that they actually have names, and the equations are quantified, if you will. Right? The paraboloid we looked at, the ellipsoid. The ellipsoid is basically an ellipse that's been spun around in three-dimensional space. Looks like a Mentos or something. We have hyperbolic paraboloids over here that look like a Pringles chip or something. The hyperboloid of two sheets, it's like two pieces. Depending on how you took your college algebra, do you remember like x squared over a minus y squared over b is equal to 1 being a hyperbola? And then when we take it into 3 dimensions, it becomes a hyperboloid. Realistically, though, as cool as it is, and as much as I like to kind of geek out on graphing these things by hand, the reality is, if someone hands you a surface and asks you to sketch the graph of that surface, what you're really going to do is you're going to go here. You're going to get an idea what it looks like. And then you're going to come back over here and sketch it. Technology has made graphing these things by hand kind of obsolete. It's similar to in algebra. When you used to graph things, when you first learned algebra, you would make a t-table and you'd pick a bunch of values for x, and then you'd find a bunch of values for y, and then you'd plot a bunch of points, and you'd say, oh, it must look like that because you plotted enough points to see the shape. That's the idea with level curves and traces, that if you have enough information, if you have enough pieces, you should be able to figure out what the three-dimensional object would look like. But just like with algebra, as soon as the math got complicated enough, this approach no longer worked. And we just used some sort of Desmos or a graphing calculator. Same thing happens. I'm going to have a hard time, unless it's a very regular, common 3D graph, I'm going to have a very, very hard time being able to look at traces and curves and figure out what it really looks like. All right, that brings us to the end of section 17.1. The next videos will be section 17.2. Have a good day.